Today we're looking at a paper that honestly tackles one of my biggest pet peeves with AI writing tools. It's called PaperDebugger, a plugin-based multi-agent system for in-editor academic writing, review, and editing.
And it really goes after that fragmentation problem. You know the drill. You're writing in Overleaf or Word, you highlight some text, copy it, jump over to a separate AI window, paste it in.
And by the time you're done, you've lost your train of thought completely. This paper, from researchers at NUS and an independent researcher, tries to kill that whole workflow.
And they do it by building an LLM agent system that lives directly inside your editor. It's a Chrome extension that hooks into Overleaf, all powered by a pretty serious Kubernetes backend.
So for you, the listener, there are two huge takeaways here. First is what they call diff-based editing. The AI doesn't just spit out a new paragraph. It gives you a patch, like a code change, that you can see and approve with one click.
Right, so no more copy-paste nightmare. And second, this thing goes way beyond just grammar. We're talking about a compare my work feature that can read a new research paper, compare it to your draft, and then generate a full citation-ready comparison table for your related work section.
Which is just a massive leap. And this isn't just a concept. They've deployed it and have real user data that we'll get into. So today, we're going to unpack the architecture that makes this all possible and see if it really solves the problem.
Let's start with that core pain point. We all use LLMs for brainstorming, for editing, but why is having that tool in another tab so damaging?
I think it's the context break. It just shatters your focus.
It's that, but it's also a technical problem. The authors point out that when you paste text into an external tool, that tool is blind. It has no idea about section 1 or a definition you set up on page 2. It's totally stateless.
And for something like academic writing, where every single revision needs to be tracked, that's a huge problem. That idea of provenance.
Absolutely. The rationale for a change, the history, it all just vanishes when you close the chat window. That's the provenance problem they're talking about. You get some text back, but you lose the why.
So PaperDebugger's whole reason for being is to fix this. It's a Chrome extension. It plugs right into Overleaf. And the goal is to let you critique and revise your work right there in context.
And the key to making that work is the output. It's not text, it's a patch, a diff. It shows you the before and after, which you can then apply directly to the LaTeX source.
Okay, I have to stop you there because this is so important. A normal LLM gives me back a whole block of text, and I have to manually figure out what it actually changed. You're saying this shows me only the specific changes.
Precisely. It turns the LLM's suggestion into a structured, deterministic edit. It's more like a collaborator suggesting a code change than a chatbot just rewriting things.
That sounds simple from my side as a user, but making that work in real time, that bidirectional sync has to be incredibly complex.
Oh, absolutely. And that brings us to the architecture. They clearly engineered this for performance and scale from day one.
Right. It's not just some simple script. They've got 5 distinct layers. Let's try to break that down.
So starting from the outside in, you have the presentation layer. That's the Chrome extension itself. It's pretty lightweight. It just injects some buttons into the Overleaf UI and grabs your selected text.
And that layer talks to the backend using gRPC. Now, for folks who aren't in that world, why gRPC instead of a normal REST API?
Speed and efficiency, basically. gRPC is built for streaming data and structured messages, which is perfect when you need to send updates back and forth in real time as the agents are working. It's just a much tighter connection.
So the extension is the lightweight bit. The real work happens in the next layer.
Exactly. The backend layer, this is written in Go, and it's all deployed on Kubernetes. You can think of this as the air traffic controller. It manages your session, figures out which model to use, and most importantly, it orchestrates all the LLM agents.
And the Kubernetes part is key for scaling, right?
It's everything for scaling. When you make a request, the backend spins up these stateless LLM agents in their own isolated pods. That means my grammar check isn't stuck in a queue behind your full document review.
So it's a classic microservices approach. That makes total sense for something where workloads can be so varied.
It's the only way to do it reliably. Then you have the agent layer itself, which is where the models actually do their thing, and that's all governed by the protocol layer, which they call extra MCP.
Extra MCP, what does that do?
Think of it as a set of rules and tools for academic writing. It ensures the agents communicate in a structured way and gives them access to specialized tools. And the communication itself uses a streaming protocol so you can actually see the steps of the reasoning process in real time.
Oh, so it's not just a spinner that says thinking for 30 seconds. You get updates along the way.
Right, which really helps with transparency. And the final bit is just the infrastructure layer, storage, CDNs, the usual stuff. But the whole design is built around one goal: generating and applying those context-aware patches instantly.
And because it's a diff, a patch, the whole interaction becomes transparent. You see the suggestion, you see the rationale, and you have final say. It makes the AI auditable.
Exactly. It's a collaboration, not a black box.
Okay, let's dive into that agent layer, because this is where it gets really interesting. It's not just one big model. They use multiple specialized agents.
Yeah, and they have two different ways of running them. For the simple, fast stuff, they use what they call prompt template agents.
And that's for things like, what, polishing a sentence?
Exactly. It's a single call to an LLM with a very structured template. It's low latency, cheap, and efficient. Perfect for a quick grammar fix.
But what about the really heavy-duty tasks, like that research comparison you mentioned?
For that, they use workflow-based agents. These are much more complex. It's a whole declared sequence of steps. Call an LLM, then run a tool to search for papers, then call another LLM to summarize, then validate the output.
And this is where that extra MCP protocol comes in. It's kind of like the playbook for these workflows.
It's the playbook, and it's also the quality control. Extra MCP enforces schemas and consistency checks to stop the agents from, hallucinating or just producing generic-sounding text. It's the guardian of the academic tone.
That's a great way to put it. So extra MCP keeps the AI from sounding like a generic chatbot.
Exactly. And it gives the agents three core toolkits. First, a pipeline for semantic search and re-ranking, which is how it does that real-time literature lookup. Second, there's a multi-step AI review pipeline.
I love this detail. It's inspired by the review process for major conferences like AAAI.
Yes, so the AI's critique is structured like a real peer review. It's not just this is good or this is bad. And third, they have their own extra GPT model suite, which are models specifically fine-tuned for scholarly writing.
So you have all these components, and then running on top are the agents themselves, the reviewer, the enhancer, the researcher. How do they all work together on a big task?
So say you ask it to review your whole introduction. A main coordinating agent gets that request. It then breaks that big job down into smaller pieces, like analyze the thesis statement, check the flow, find supporting literature.
And it sends those smaller jobs out to different worker pods on Kubernetes.
In parallel. And once all those little jobs are done, the coordinating agent gathers up all the results, merges them, and presents you with one single structured report. That's how they get both speed and depth.
Which brings us to the real-world use cases. This isn't just theory, it's a deployed system. Let's walk through that micro-level patch workflow.
Okay, so picture this. You're in Overleaf. You've written a section title that feels a bit clunky. You highlight it and ask PaperDebugger for a rewrite.
And in the background, that kicks off a whole pipeline.
A whole pipeline. The critique agent figures out why it's clunky, the enhancer agent brainstorms better options, and the patch generator creates the diff. What you see is a simple before and after comparison.
And crucially, you also see the rationale for the change. You're not just blindly accepting it.
Right. It's informed consent. You review the reasoning, check the diff, and if you like it, you click apply. The whole destructive copy-paste cycle is just gone.
Okay, that's the micro level. Now for the feature that I think changes the game. The deep research and comparative analysis.
This is where it goes from a writing assistant to more of a research partner. So you highlight your related work section and hit deep research.
And that triggers the full extra MCP retrieval pipeline. It's searching RCV, Semantic Scholar, all of it.
And it comes back with a ranked list of relevant papers. But it's not just a list of titles. For each one, an LLM has generated a little summary of why it's relevant to what you wrote.
That's already incredibly useful. But the Compare My Work tool is the magic trick.
It really is. You pick one of those new papers, and the system invokes agents to read that paper and to read your draft. It then automatically extracts the core components from both the goals, methods, limitations, everything.
And it synthesizes all of that into, what, a paragraph?
Better. A structured side-by-side comparison table, fully citation ready, that you can insert directly into your manuscript with a click. It does the tedious synthesis work for you.
That is genuinely incredible. It's not just generating text, it's architecting knowledge. It's doing the hard part of writing a lit review.
And this is where all that complex back-end engineering really pays off for the user. It allows the LLM to deliver highly structured, synthesized data, not just prose.
The tech is clearly impressive, but what about the users? They provided some early telemetry. What does it tell us?
Well, the numbers are pretty strong for a niche academic tool. They had about 78 registered users, with 23 of them active monthly. That's a retention rate of around 30%, which is quite high.
And they were clearly using it for real work. Over 150 projects, nearly 800 writing threads. This isn't just people kicking the tires.
No, this is sustained engagement, but the really fascinating part is the interaction patterns, the event logs.
That's the key stat there.
It's the ratio. The number of times a user clicked diff viewed was over 1,000. The number of times they actually clicked insert patch was only 359.
Wow, so that's almost a 3-to-1 ratio of viewing a suggestion versus accepting it. What does that tell you?
It tells me that users are being incredibly deliberate. They aren't just blindly trusting the AI. They are using the diff view as their main control surface to critically inspect and often reject the AI's suggestions.
So their central design choice making the patch, the core interaction, was completely validated. Users want the help, but they absolutely demand the final say.
100%. They're treating it like a collaborator whose work needs to be checked, not an oracle.
Yeah, what about the qualitative feedback? Any complaints?
The feedback was mostly positive on the convenience and the seamless integration. The main critiques were pretty predictable, actually. Some said the suggestions felt a bit too CS-like in tone, which means they need to do more fine-tuning for different academic domains.
Sure, a biology paper sounds very different from a computer science paper.
Exactly, and some users noted performance drops on very, very long documents, which is a classic context window challenge. But overall, the data shows the core concept is working.
So to wrap this all up, PaperDebugger feels like a really significant step. They've built a truly integrated in-editor environment that bridges the gap between our documents and our AI tools.
Absolutely. The technical architecture with Kubernetes and the extra MCP toolchain proves that you can build a scalable, reliable system for this. It sets a new bar for what a writing assistant can be.
Which brings us to our final thought. This move from an external tool to an integrated, context-aware agent that operates directly on your source code. That's a fundamental shift in the writing process.
It really is, and it makes you wonder, if these agents can reliably handle this level of critique, literature synthesis, and structured editing, all through inspectable patches, how far are we really from a future where the first draft is just an orchestration of these specialized agents? A future where the human author's job becomes less about writing prose and more about high-level strategic direction and just validating patches. It really starts to blur the lines of what authorship even means.